Okay, so let's start. So it's really my great pleasure to welcome here today Eugen Ruška. So just to say a few words about him. So he's currently principal investigator and assistant professor in the Department of Biophysics and Physical Chemistry at the Faculty of Pharmacy in Hradec Králové Charles University. And before that, he was a postdoctoral fellow at the Emory University in the US. Before that, he did his PhD in physics at the Rice University in the US, and with the focus on adaptive sampling of conformational dynamics of proteins. And before that, he did his bachelor in biochemistry in Germany, in Regensburg. So how we met, so Eugen was very kind to do the mid-PhD review of the PhD thesis of Petr Kouba, so that we met and interacted, and he got very useful comments on Petr's work from Eugen. So we thought it would be great to get more comments on what we are doing and maybe discuss potential opportunities for collaborations. So here Eugen is, I'm very excited to hear more about what he's doing in the exploration-exploitation trade-offs for protein conformations and dynamics. Eugen, the floor is yours. Thank you very much for coming today.
Well, thank you for inviting me. And I want to talk about something that is kind of crossing different faculties. It's crossing from pharmacy, chemistry, and physics, and also computational aspects. So sometimes there's like a different understanding what is the motivation and what is important in different areas. So hopefully this talk will help with that. And I want to focus on protein conformations and dynamics. So just as a short repetition, for proteins, we can have static and dynamic representations. So static is like X-ray crystal structures, where you have one three-dimensional structure, and that represents the protein. So example for that is AlphaFold and OpenFold. You can also represent it as more conformations. So for example, apo and holo is when you add a ligand, it changes somewhat the structure. It's not exactly the same. It changes somewhat. And there, that's important for pharmacy, obviously, when we develop some kind of drugs which interact with the protein. And there's not only two of them. If you're accurate enough, typically you have some kind of multiple states, a conformation. If you're accurate enough, it has a whole distribution across the whole landscape. It's not always measurable in the experiments, because sometimes the experiment is really like a very deep minimum. But sometimes, like in the intrinsically disordered proteins, it's really a distribution which is measurable. Sometimes there are two states easily measurable in experiments, but this is like the computational aspects of it, and you can have like thousands or millions, in theory, infinite number of conformations for each atom. Yeah.
So I'll just briefly interrupt for those. I see people who are not working proteins. So just to vocabulary for us, it is also a conformation is a shape of the protein. The protein can have multiple shapes. These are called conformations. And the other word which I struggled with was ligand. So ligand is referred to a small molecule. We can think of it as a drug candidate, much smaller in the protein, and it can change adding the ligand can bind to the protein, can change the shape. That's why ligands, the small molecules, can change the conformations. Sorry for the interruption, but that's something I struggle with for a while. That's why I'm trying to explain. Thank you. Sorry.
Yes.
You are speaking about distribution, but I think that actually the protein can be in different shapes or conformations. And distribution means that frequently it's in this shape or in that shape. But it very much depends on, let's say, whether it's in liquid or something like this. So I don't understand.
So this distribution is the equilibrium. If you leave it in water, it's, let's say, 20% in this minimum, and 50% in this minimum, and 10% in this. So it's an equilibrium where it's very fast in a millisecond.
Under certain situation, like in water.
Yes.
When it's dissolved in water, then we can speak about distribution. Okay.
Yes. It's like sometimes it's very narrow distribution, but generally you can assume So the time scales are quite fast. So the third one is actually the dynamics. So if you measure some kind of information over time in very short time scale, milliseconds, biologically relevant, you will see that this protein, which x-axis is time, y-axis is some kind of dynamics or state information. It's going from one state, then jump to another state, and then jump back, then stay in one state, jump. So this is the actual dynamics. So this is what would happen in water, and some proteins will stay only in one, but some proteins will jump. One of them might be apo, one other might be holo with the ligand. So the different conformation might look differently, but by the distribution, I mean that if you average over, let's say, a second, what will be the distribution of this protein?
And actually, when we are speaking about those conformations, the molecule has some number of degrees of freedom.
Yes,
Like
I will come to that. Yes.
The thin lines means that you can rotate.
Yes.
Around it. So that means that the dimension of this middle graph is actually.
Yes, yeah, I will come to that.
Okay.
It's a great point. Yes.
Is about the protein ever stop between the states? You let it sit for long enough.
No, this is the equilibrium. So I will come why that is. So why the reason is, it's physics. So if you have some kind of system which can have multiple states, then we figure out that the Boltzmann distribution describes the probability of the system in each state. So we will have n different states. For each state, we will have energy AI, some temperature. So this is assuming we have temperature. If I have 0 kelvins, it will stay in one state. But in pharmacy, we don't really care about 0 Kelvin. We care about room temperature or body temperature. So this is actually a significant distribution, a significant tail. So depending on the temperature, you have exponential. So the higher the energy of a state is, the lower the probability it is. And this exponential decreases quite fast. But since the timescales are so fast, like milliseconds, it means even if the probability is like 10 to the minus 4 of transition, it will still happen in biologically relevant timescales. So this is the general physics. And if you have the energy of a state, you can calculate quite precisely the probability. So if we take all the conformations, so it's still a simplification. If we put all the conformations, then this is how it kind of looks like. So the x-axis are the different conformations, y-axis is the energy, and the higher the energy, the less probable it is. So generally, the ground state is somewhere here. There might be some kind of split of the ground state somewhat. Sometimes they are just one, and that's where most of the time the protein stays. And sometimes it can transition across a high energy barrier. Let's say it folds or unfolds or something like that. A very high energy barrier, the probability is very small in like millisecond timescales, and then it crosses and the energy is again smaller. And if the protein is here, it will stay here for a while. And that's how you get like the state dynamics. It will stay for a while here, then rapidly cross, stay for a while here, rapidly cross. Yes?
Temporal, with high temporal. I mean, why is this sudden position happening?
I will come to that. I will come to that. So why? So if you calculate the energy of a molecule, let's say we have n atoms, and you can, due to the Schrödinger equation for the electrons, we can calculate the exact energy of this state. So this depends on the x. X is the position of each atom, the nuclei, where it is. And for each of these like n positions of nuclei, we can calculate the energy. There's some kind of quantum kinetic quantum effects, and you will have some kind of energy for each of these positions. if you move one atom, energy will change. So that's why I mentioned that for each conformation, you will have a different energy. So this is like the theoretical aspect. In experiments, if the probability is very small, you might not measure it. So there's some kind of challenge to measure the high energy states. The problem with Schrödinger equation is we cannot really solve it. For the electrons in high accuracy, we can solve it high accuracy almost exactly with CTS dt, which scales as number of atoms to the 7. So this is only useful for like 5 atoms. This is not useful for biological system with thousands of atoms. Slightly better scaling and to the roughly 3 is density functional theory, which still doesn't scale linearly. So you will get stuck at around 1,000 atoms, but that's already a small protein. So it's kind of biologically relevant, but not for all systems. But still, it's very, very slow. You can fit, like if you fit these energies for different positions with the force field, so you just take the distance of the bond, distance of angles, dihedrals, and so on, you can approximate it. It's much faster because you don't have to solve this complicated equation, but somewhat inaccurate. And even the fitting introduced some inaccuracy. There are different aspects of it. Let's approximate this as accurate enough. Once you have these positions, so energy depending on the position of all nuclei for this time step, we can calculate the acceleration. And with integration, we can update the positions from time step t to time step with the small time step, update the positions. The problem here is that the time step has to be very small in the femtosecond range so that we don't have excessive numerical integration errors. Yes.
This is great, very nice. So this would be what's U here?
That's the energy of the state, and we take the gradient.
Okay, so it's the energy of this.
Yeah, energy of all and atom and nuclei positions.
Okay, so the gradient of the energy, the acceleration of, and it will be acceleration of, this is like per atom measure, but it's all atoms.
Yes, it's a vector. It's slightly thicker, so it's a vector. Every atom will have an acceleration on it, and every atom will have a velocity in it, and every atom will have a position, and it will change over time. So at that point, you will have the trajectory. The velocity is generally not that important. There's a Born-Oppenheimer approximation that we can decouple the position of what the electrons are doing, the Schrödinger equation, from what the nuclei are doing. So generally, we just look at the positions, how they behave. But still, it's very complicated because this is a vector over all atoms. So we have thousands of atoms.
So for 1,000 atoms, it will be a 3,000
Yes.
dimensional vector.
Yes, exactly. And over time, it changes. So there's a lot of information in this trajectory, assuming we can simulate the trajectory good enough. But even with the trajectory, you still have to analyze it. So with all this, how far can we get? So DFT is slow, so we can get into range of picosecond with GPUs, with molecular mechanics somewhat faster, into milliseconds in the custom, depending how accurate you want to be. When we compare that with biological relevant things, we have vibration, we can simulate that quite well. Water dynamics, we can simulate that on quantum accuracy. Chemical reactions are on the edge of actually simulating that in that sense. So typically chemical reactions are not simulated in molecular dynamics, but we are getting there. Very fast biological events like very small peptide moving, that's well inside of the molecular mechanics, but it's outside of quantum accuracy. So we are losing somewhat the accuracy there. Then more complex like lighting binding is on the upper edge of what molecular mechanics can reach, the milliseconds. It's a logarithmic axis. So if you improve by a factor 10, it's not really a big difference, actually. You need to improve by a factor of 1,000 to make like biologically different processes visible. So millisecond here, ligand binding. Protein folding goes from milliseconds to seconds. So depending which protein, you might be able to simulate it, larger ones not. Aggregation is also generally outside, like the timescale, the biological timescales are in seconds. So whatever you measure experimentally, which takes longer than a millisecond, it's extremely hard to simulate. So this is kind of the challenge. That's why having a large data set of experimental data, like the crystal structure, is very advantageous because it's kind of compressing a lot of information there. If you don't have this data set, you have to do essentially from the physics-driven simulation, and that's hard, or it's slow, let's say. All right, so this is the overview. Depending on which biological system case you want to simulate, it takes long, and this is just for one simulation. So here, I wanted to explore how far we can push that. So I took a bunch of systems where we had a benchmark simulation by a D-show from 10 amino acids. So this is not, it's kind of like tiny peptide. It's IDP-like, all the way to 70 amino acids, which already has a couple of coils. So it's a small protein, but that's how far I was able to push the boundary of simulating the whole dynamics. So getting the one structure, the static information, we can do with machine learning. To get the dynamics of the whole conformation, which all averaged over the second, there's very little experimental data, and simulating it physics-based is also hard. But so this talk is about how to push this physics-driven simulation further. So if you do brute force, by that I mean a supercomputer with 100 GPUs running for a week or longer, and just simulate it. You start with some kind of unfolded state, just random stuff, and wait till you find all the distribution. Somewhere there's the folded state, which we know there's experimentally determined, so we can check if we actually got the whole distribution. For 3 out of the 4 proteins, up to here below 28 amino acids, brute force, we can do that, but that's like 100 of GPUs for weeks. Yes?
There are few local minima, and you call some of them you call folded. What is the difference between the, let's say, the right one and the right one which is folded?
Okay, so let's explain the color coding on this plots. So the colors go from black, which is the lowest energy, the highest probability for that spot to be. So it's actually free energy. It's kind of dimension reduced, but I will introduce dimension reduction in a second. And red is very low probability to be in this pixel. So folded that's what has the highest probability. And these are proteins which fold. Some peptides just don't fold. They are IDPs. They just are distributed over this. But if you crystallize it, it will kind of low temperature, low energy, it will drop into the high probability state. But here we go across many orders of magnitude of probability distribution. So the red parts are like 10 to the minus 5, 6, 7 probability compared. So it's a very small probability, hard to measure experimentally. Only if you have like another minimum somewhere here, like, then that's actually something you might be able to measure. So experiments like FRED, where you see like 2 states and they interconvert at a very fast time scale. Sometimes there are like multiple minimas. It's kind of hard to determine because we are reducing the whole atom, all atom positions, sometimes hundreds, thousands of atoms into one position. So what we want to do is actually improve our sampling. So brute force, we cannot afford just to spend like weeks on hundreds of GPUs for each biological case. So we need to speed it up. So why is it so slow? Most of the time, this molecular dynamics trajectory, this numerical integration we do is spent here. The probability here is the largest. And if it goes up the hill, then the probability drops rapidly, exponentially. So here is like factor 10 smaller, then 100, 1,000, and so on. So the probability to get here is extremely small, but it's not zero. And after millions of steps, it might cross and be here. But so there are a lot of strategies how to make it more efficient, because just running the integration might not, in this area, we are not learning anything just by running it. So what if we somehow use this information and explore it here and solve this integration in this area, spend more resources there? So there are many different strategies, and I explored one of them. There are many which like add some force to external, like artificial force to the system. I did not explore that because there are some, it's harder to then get back the Boltzmann distribution, the actual average, which average distribution and the kinetics from this kind of data. So I just use unbiased simulation, this normal integration. What I did is where you start. So every integration, you have a starting point. So this starting point is like the X, Y, Z positions of each nuclei, and you can pick that. If you pick it well, you're kind of halfway up the hill. Then you pick second time on the hill and so on. So that's kind of, if you simulate starting here, then it will rapidly explore this area. So this kind of the general idea of adaptive sampling. So now I come actually to the problem of having hundreds of thousands of nuclei. Each of them has a X and Y and Z position. How to represent it? That's just too much information. So to think about it, you have to simplify it. We are not computers. So it's called also the curse of dimensionality, where we have 3n minus 6 degrees of freedom for n atoms. So if you rotate this, so 3n is for X, Y, and Z. 6 is because if you translate it and rotate your protein, it's still the same biological system. And all these degrees of freedom, you can mathematically calculate it, but it's hard to think about it. So if you measure some kind of distance, for example, here and here, which could, for example, infrared represent the folding, unfolding event, this distance looks like this. So I mentioned that before, but you can have like a lot of distance, a lot of angles. And this kind of makes it more easier to understand that you can think about angles and distances easier than just X and Y and Z positions, but that's still too many. There are hundreds of angles, dihedrals, and so on. So to get around that, to reduce this into, let's say, 2 dimensions to make plots, or let's say 3 or 4 dimensions to somehow have the same, almost the same information with minimal information loss. So if you don't have proteins, you might do PCA. In proteins, we have kinetic information. We don't want to lose that. Like this timescales, the dynamics is very important. We might not care about something which is very fast, just a hydrogen atom moving. We care about the very slow processes, which computationally we cannot really resolve. So this dimension reduction is kind of similar like PCA, just adding the kinetic information. It's called TICA. It's also linear. And what we do is the covariance matrix of distances. So we take distances over time and compare it with distance plus a time lag. So the time lag is the kinetic information. We get the matrix, how these distances correlate between each other. And when we do something similar to PCA, generalize the eigenvector problem, we get eigenvectors and eigenvalues. Eigenvectors, the slowest ones will contain the slowest timescales in this linear space. So it's somewhat limited, but still the slowest ones. And that's generally useful for biological cases. Sometimes the biological process is not the slowest one. So you have to be sometimes careful. And it's not, you lose some kind of information. So if you reduce it to 2 dimensions in this eigenvector space, you might lose some information, but most of the information is generally. All right, so we reduce it in this space. So this TK, this axis are the position on the vector. So each dot is like the transformation of x, y, z coordinates into 2 coordinates. And the trajectory is like moving in this space. All right. We are still not finished because proteins are nonlinear. This was linear, easy to calculate. Proteins are nonlinear, so one of the ways to represent this nonlinearity are Markov state models, where you divide your states. So let's say this, we split it, let's say into folded, unfolded, and misfolded states. And you can calculate the probability of transition after a certain time. So this Markov state model would represent A, B, C, D, and each is like a part of this landscape. And the protein will kind of jump from one to another with a certain probability distribution. And we can get that from a trajectory. We cannot do that really from experiments. And if you do computational, you can have very fine states. If you have very large states, you might lose some kind of information. So generally, I took somewhat like 100 up to 1,000 states, like separating the whole landscape. And then you have a transition matrix where from the trajectory, you estimate the probability from jumping from A to B and so on. And that will give you, from the advantage of this is you can run, you can analyze the non-equilibrated trajectories. So if you run a short trajectory, like not infinite, then it might not reach the whole Boltzmann distribution. So from this short trajectory, it will just cover a part of this landscape. To combine, but you might just do it in parallel on a supercomputer, and you will have hundreds of these trajectories. To combine that, Markov state model is good for that. It will give you a stationary distribution, even from these non-equilibrium trajectories. It will give you also kinetics. There is a deep learning version of that, where the combination of TK and Markov state modeling is kind of done in a hidden neural network. You have also the covariance. So the TK, it's the same covariance, but before we had distances, like physics inspired features put into the covariance. Here we have some kind of hidden neural network which transforms our XYZ positions into this covariance. So some of you might be well aware of that. So just I will not go much further in this. You minimize the loss, which represents this kinetic information in that. But I want to go into the exploration part. So for that, we had the problem that we are stuck in this minimum and very rare getting over this hill. So what we have actually in a supercomputer, if you run parallel simulations, let's say we run 4 trajectories and 3 will be stuck. And here we have too much data, it's oversampled, and we already have enough data about that. But one of these trajectories is interesting. It explores something new. It pushes the boundary where we were. So maybe it goes slightly up. It goes here. It's not the whole biological process, but it goes up here. And due to the previous dimension reduction, we figured out that that's somewhere on the edge of our map. It's like map where we have clouds or fog, and we kind of push the fog away. And this is like pushing the furthest. All right. So we have this 4 structures. We don't really need more information here. So adaptive sampling. So here we have the problem of multi-arm bandit because we have 4 structures or 4 clusters in Markov state model, and we can spend our resources in different ways. We don't have to just simply integrate. We can restart in a cluster and add more trajectories there. So let's say we have a full Markov state model, which is in real like hundreds of these clusters, A, C, B, D, and B is not yet explored. We want to find this. It might be some interesting state. So we have currently explored these three states, and due to the Markov state model, we can estimate the probability to find the new state, to cross, and only these arrows, this arrow is actually will find the new state. So the probability to find a new state is 0, 0 here, and here a small number. It's still, you need to get stochastic and average, and after many tries, like long trajectory, you will get a probability to cross this hill. So this hill, the probability to cross some kind of hill, something like that. So this is also called the multi-arm bandit problem, where we have different clusters and you can spend computational resources. You have finite computational resources. How do we spend it? And the problem, the dilemma is here that we don't know the probabilities. If we knew the probabilities, we can just take the maximum and we are finished. Unfortunately, we don't know these probabilities. So we can just, if we just randomly put our resources, we will estimate these probabilities just by sampling. So we have two strategies, the exploration and exploitation. Exploration is estimating the probabilities, exploitation, picking the highest probabilities to get a new state. So this is in short the multi-arm bandit problem. So what the title of the talk is, and one of the approaches. There's many approaches because this problem happens in different areas, not only in proteins. You can pick the state among the already explored, which is inverse to the count of already how many times we visited it. So the how many times we already visited it is an estimate of like accuracy of the probability. So because of stochastic, if you independently measure some kind of value, the more times you measure, the more accurate it is. So just very rough estimate, inverse of this number is the accuracy, how accurate we have this probability estimated. And then we pick the state according to that. So basically, if we have a state where we only have one visit, we don't know the probability, what will happen if we run it. So it's a good idea to spend more resources there. If we have a state, let's say D, where we already have hundreds of hours of simulation there, the probability that we'll find something new is not 0 because it's a high dimensional space, but it's very small. We already know that because after a certain time, these trajectories are decorrelated. So this approach, also adaptive sampling, I tried that and it looks like this. After every iteration, we either stop these trajectories because it's already high probability, and due to this multi-arm bandit approach, we will spend more resources here. We bet essentially that if we spend resources here, we'll get something interesting. And then we run for a while. We cannot run for like just a femtosecond because biologically nothing interesting will happen. The probability of finding new things is very small. So we have to run, let's say, nanosecond or something like that. So there's a correlation time. And after a while, we estimate again, did we find a new state or so on? Getting this dimension induction takes a tiny time as well. So yes.
So you build the Markov state model as you go?
Yes, yes. It's on the fly. Unfortunately, it's like a map with fog on it. At the beginning, we have just random or some kind of experimental, or we start with AlphaFold conformation, and everything else we don't know. It's like high dimensional space. So we can technically enumerate it, but we cannot enumerate 1,000 atoms in 3 dimensions. So it's just too many possibilities to enumerate. So we don't know which of these are the important ones. So we kind of go on the go. We kind of, these kind of finding a new state is like, it will explore a new part of the map. But we only explore a tiny part. And then we go iteratively to explore the map.
So if it's sort of sufficiently far from what you explore, you just call that state and you call that configuration and you state, or do you actually use some kind of a VAMPnet-like approach to build it?
Yeah, I used the VAMPnet. So all these dimension reduction, the TICA, the Markov state model, and this deep learning version of TK with Markov state model is exactly how you define the states. So
But you
these
have
are
online version that you build it as
yes,
you go.
yes,
you build-
iteratively, yes.
Okay.
Unfortunately, we don't have already infinite trajectories, so we generally don't know the states a priori. So we take this already found map and build the states on it. And based on this information, we use this information to explore the map further. So it's on the fly, it's iteratively. If we had the whole map, we could find the states in the final version. So if we just take this partial length map, the state definition will be not complete. So we will have only, let's say, this part, and B is not even on our map. It will be not part. So these are not converged Markov state models. They are on the fly. That's why it's iteratively run around 20 to 50 iterations. But that depends on the state. So you might be aware of this adaptive sampling. So there are different software on it. So the one, and at some point you realize you're not exploring anything more interesting. Unfortunately, it's like high dimensional space. So you cannot be 100% sure you found everything. Or you found a biologically interesting event, and then you stop. So the way computationally, how it looks like, you start with some kind of initialization, either random experiment or AlphaFold. You simulate some short trajectories. You analyze to get the on-the-fly state definitions. And if you're not finished, then take this exploration-exploitation approach to prioritize different states and then simulate another batch of trajectories in there. So computationally, it looks like this. The software I used it to run was in Python with some collaborators to run it on a supercomputer. So we want to be efficient. So it's kind of Python wrapper around this distribution of tasks. So this heterogeneous workflow, we have MD trajectories and analysis. And we have to decide what to do next. So these essentially two tasks, MD and analysis restart, have to be scheduled at different times. So we have these Python things. And over the time, we got better to actually scheduling it. At the beginning, we just run MD. At some point, once we finished all the MDs, we analyze it. It might take a couple of minutes or depending on your data. And during that time on the supercomputer, all the other GPUs, they're just waiting, not efficient. So instead, in the version 2, we run parallel analysis and MD. This kind of means that if you restart your trajectory, it's using an old analysis. It's not like using the restarting information of all the molecular dynamics, but it's using a somewhat old on-the-fly analysis because the analysis itself takes a couple of minutes, sometimes a half an hour. But running in the parallel makes the computational efficiency higher. And that's how we got to scaling to roughly 2,000 GPUs. So the software scaling. So here we are measuring the efficiency, the percentage of time where we actually run anything like the task which we want to run. It's a heterogeneous workflow, so we cannot really do weak scaling or strong scaling. And not communication. So here at 2000 GPUs, we have too much communication. So this is the software, but there's a different scaling, the scaling of the algorithm, because we have this exploration-exploitation strategy. The more trajectories you run in parallel, the less efficient this information is. Because if you would run each trajectory separately, you could use the maximum of this information to get the new restart trajectories. But we are not on a supercomputer running parallel, 50 GPUs or something. And that's why we don't use the maximum of this information. And it scales up to 100 parallel trajectories, 100 GPUs of this algorithmic algorithm. And then it's getting less efficient. Interestingly enough, so just brute force molecular dynamics is the least scaling. It's not sharing any information. So it's just independent and there's no information sharing. So it's less scalable. It's not as efficient. But with these, you bottom out at around 100 for larger proteins, 1,000 GPUs. So what I compared here are different of these exploration exploitation strategies to figure out which one is actually the best. I will mention about that.
Can you maybe explain the graph sorry about this? So what the on the axis is trajectories and what's on the y-axis?
I will come to that. So in terms, it's like a simulation because each of these folding events takes several weeks on like 100 GPUs, too expensive to compare different strategies. So for that, I took like a Markov state model and simulated how long it will take to fold for this kind of computational model and applied the different strategies, just brute force or different exploration exploitation strategies, and compared at different parallelizations, how long it will take. And at some point, you're not improving anymore. And that means just parallelizing more, just wasting your resources.
So lower is better.
Yes, yes, lower is better. And I will talk more about this in a second. So there is a software background to actually run it on 2000 GPUs and not wasting too much time on communication, but that was done mostly by collaborators. At the end, there's a software package, so it's a competitor to other adaptive sampling softwares which do similar things. This is asynchronous, which is maybe the biggest advantage, where I mentioned that the GPU is never waiting for instructions. It uses the latest instruction, which might be already a couple of minutes old, but it's still the latest instructions and can combine it with WAMPnet. So all these things were done with WAMPnet. So with that approach, we finally got to the fourth protein. So remember at the beginning, we had the 4 protein as a benchmark. With brute force, we can get to 3. The largest one with 73 amino acids, we only get with the speed up with this kind of exploration exploitation strategy. So with brute force, what happened? We just run out of time. So we have finite computational allocation. It just run out of this allocation. If we spend more allocation, maybe it will fold at some point. But there is a speed up. So the x-axis is time. So that's kind of the estimate of computational resources. And the red part is for this adaptive, this exploration exploitation strategy. And the red line is where we find the folded state. So we start somewhere random conformation. And at some point we find the folded state, which we assume is the biologically interesting state. And we measure how long it takes. So here it took this long. And for the blue, the brute force, it took more than 7 times longer. We run out of allocation at that point. So this is not yet kinetics. This is just like exploring the map and finding a sample of conformation. So there are many of these X, Y, Z conformations, which experimentally you might not be able to resolve, but are part of this distribution of which is what the protein is doing average over, let's say, a second. So the kinetics actually is how fast this protein in this trajectory is going from state A to B, folded, unfolded, or able binding of this ligand or something like that. So this time and these eigenvectors in this map, that's the kinetics, the dynamics. And here we could look how accurate is this time, the mean first passage time over our simulation time. At the beginning, we didn't find this state at all, so we cannot calculate this time. At some point, we found this state, but the dynamics is not accurate enough. We didn't sample this transition region accurate enough. And this time estimation will improve. So you might notice that the y-axis is logarithmic and the kinetic is notoriously harder to converge than just the map, the landscape. the ensemble of structures. So what here also there's some more comparisons over the benchmark. So the 4 proteins, blue is always brute force, red is the exploration-exploitation, and the gap on the logarithmic x-axis is the speed up, how much resources we save. And the factor is somewhere like between 2 and 7, which is not massive, but I will investigate that further. Yeah.
And so the vertical bars are what are the times when it reached the
Yes.
folded state?
Yes.
Folded state.
Yes.
So you want the bigger the gap between the two, the better.
Yes, yes, yes. If we find a biological state, we can analyze it. If we don't find it, we cannot do anything about that. Yes.
And how you know that this is a folded state?
So in this case, it's a benchmark. So we have defined experimental structures.
Before.
Yes, beforehand for this benchmark. So we can analyze if it's correct or not. In many cases, you might not know because it doesn't crystallize or something like that. And then what you do is you just look at your map and you wait till it does not improve anymore, or you know for some kind of biological intuition that how it should look like, some other experiments, and you kind of check if all the other experimental data is matching with the map, is somewhere on the map. If it's not on the map, you know it's something missing. But in this benchmark, we already know the solution, so we can check how fast we find it. Yes. All right, so here's the actual kinetics, the dynamics, which is much harder to do than just find a second structure, a conformation. And depending on the protein, it might be like at the beginning might be 1,000 times off. But when we add more data, it's getting closer to the reference value, but it's still not particularly accurate. So there's room for improvement here. And you might notice here, if you don't reach the state for the brute force, you cannot estimate the kinetics at all.
So the horizontal dashed line is the reference.
Yes, it's the benchmark. Yes, and this can be sometimes experimentally measured, red or something like that, but not always. It's quite hard experiment to estimate these things because it depends on your state definition. Notice that the state definition previously, everything was computational state definition. The experimentalists have a different state definition, which depends on their resolution of the experiments. So they might only have 2 states, apolar or something like that. And then the state definition is very broad. Here we have small states because we are computational, but you can coarsen it to have like similar state definition as the experimentalists. Yes.
So how can you estimate the time rates, like the MFPT from the bias simulations?
So there are no bias simulations here. So we only the adaptive sampling is where you start, but actual simulation is unbiased. So this is a difference to metadynamics, for example, or replica exchange or something like that, which has the advantage that these kinetic information are easier to extract. So what we do is build this Markov state model, and we have these kind of transition probabilities. And from this matrix of transition probabilities, we can estimate the eigenvector, eigenvalue. We have the timescales of what is happening there. We can even define different parts of the map states to what actually is biologically relevant and measure the mean first passage time when you start in state A, how long it takes on average to first find state B. But you can do that from here, computationally.
Yeah, but if I'm like pre-selecting the starting points, so like I'm doing this like the pruning, then like the ensemble is somehow like biased, you know?
Yes. But that's the advantage of a Markov state model. To some approximation, the Markov property. So the Markov property, if you don't have Markov property, you cannot build Markov state model, that your probability of transition does not depend on your history. So conveniently, the memory of your state, like there are many memories like velocity and so on, but they are generally a very short time scale and it depends on your state definition and so on. But if you can just model your transition probabilities not depending on your history, but only on your last step, then you don't need your history. You don't care what if you just started or you run for a long trajectory. So this is the advantage of Markov state model, and then you can combine these kind of short trajectories. So your question is definitely very important, because if you run a short trajectory, it's not sampling the whole thing, not the Boltzmann distribution, which you expect to find. So you have just an aspect of it, and you kind of merge all of it with this Markov property assumption. You have to check it if it's actually correct, but to some extent it works.
Thank you.
All right, so here we have the kinetics. So that's how far I got. There's room to improve. As far as I know, there are some attempts to do similar benchmarking for metadynamics or some other like sampling approaches, but I have not, like these speedups sometimes are claimed to be higher, like 100, if the system is very small. So if you have a system of, let's say, 10 atoms, the speedup might be much higher. So this system is more effective when it's diffusion limited. If your system is like has a high energy barrier, it's kind of ballistic, then you need this force to overcome this barrier. It will not help you to restart. So there's this kind of memory, and this kind of adding artificial force will is more efficient in that case. But the actual comparison of how it scales with the size of the system, because remember, 70 amino acids is not the size of most of the biologically relevant systems. These are much larger. So we have room to go. And how it scales from tiny system, toy models, to more relevant models, the scaling is shown here. And to further investigate how this algorithm, this exploration-exploitation algorithm scales, I compared different strategies, and based on the Markov chain trajectories. So we take this, in this case, we assume we know this Markov state model. And based on this ground truth, we kind of model what the supercomputer would do with much less computation costs. So we take this Markov state model and run Markov chain trajectories on that, just kind of approximation of the actual numerical integration of this whole protein. But it allows us to compare different parallelizations of the Markov chain trajectories, allows us to resample like this exploration-exploitation strategies, and we can average. If a simulation takes weeks, we cannot just repeat it 100 times to average it and get some statistics. So we have some starts. So essentially all the steps are done the same way, except it's not actual simulation of protein, it's just simulation of this Markov state model. And the first strategy, this inverse of the count, is the microcount strategy. And here we have some kind of count, how many times independently we visited the count, and the restart probability, which is the inverse, which is trying to solve this exploration-exploitation problem, looks the opposite, inverse. So this is the probability, and that's where we pick our new starting states of the Markov chain trajectory. And we run the Markov chain trajectory again. We have these transition probabilities, and we can analyze it the same way. Did we find the state which we are interested in? There was other strategies which I compared with, macro state strategies. You may remember that on this map, everything is kinetically somehow connected. So if the states, I picked like 100,000 small state, microstates, but neighboring states might be very close, kinetically very close to each other. So if you do a second step where you cluster these small states into bigger states, more representative of experimental states, then you do another exploration-exploitation step where you estimate the optimal restarting probability. And that's the second strategy which I compared with. And this one was the actual strategy which I used in the main simulation of the benchmark of the proteins. There are many small options like the number of macrostates and some kind of how much kinetic information we do between macrostates and microstates, corrections, all these things. So what we do get, so as is different strategies, and for each strategy we get the average number of steps in this Markov chain twofold. So the fold is like finding a specific state, and it's stochastic, so we have some kind of uncertainty, and the MD is one of the longest. It's not efficient, and depending on the protein, so each protein has a different Markov state model. Depending on the exact parameters, it might improve. So here, there's the these parts are where we cluster microstates into macrostates to exploit more of this kinetic information to optimize the exploration-exploitation strategy. These parts are where we know in which direction we should go. Let's say the experimentalists have some kind of idea that this distance should be shorter. We can use that as a biasing step, not as an external force bias, but as a restarting bias. And that improves depending on how accurate your information is, that this distance should be shorter. Then also compared with the optimum strategy. Previously, there was no idea how good this strategy can be in the case of proteins. So and then I will mention how I constructed this upper limit on this approach. And you can see that the ratio between the upper limit and MD is significant. The ratio between the actual strategy we can implement without experimental information is just like 4, maybe 10. If we have experimental information, another factor of 2, depending on your protein. So sometimes more, sometimes less. We can also compare with how many parallel trajectories we run. So if we run parallel Markov chain trajectories, how long does it take to actually find this folded state? So of course, more calculations, faster, but at some point it just bottoms out, because if the probability go directly from start to end is very small. So independently how many parallel trajectories you run, it will take a certain time. So that's why it bottoms out. The scaling is worse for molecular dynamics and for these strategies which share information between the different trajectories. So this is the absolute time, the time for the real world representing time. The total time is kind of the computational resources. If you parallelize it, the computational resources increase. So at so below the scaling limit, it's kind of flat. And at some point, it just increases. So it's not efficient use of your computational resources. That's why I said that the algorithm scales to roughly 100, maybe 1,000, depending on the size of your protein. So the actual speed up depends on your system. So from these Markov chain trajectories, I compared the speed up between brute force molecular dynamics and this kind of adaptive sampling, depending on the complexity of the protein. So very small toy model might not be very high energy barrier or be hard to fold. And there's no advantage really, because there's no barrier to cross. So the speed up might be just 2, but if you increase this mean first passage time folding, just more complex, more rough energy barrier, the speed up increases to 10, maybe slightly more. And the hope is, but it's not proven, that since the biological systems are the actual most biological systems are more complex than these benchmark proteins, that the speed up will further increase. That depends on the actual strategy. So this is the upper limit. Upper limit is factor 10, maybe 20. The actual strategy has a speed up between 2 and 7, which represent, so this is the estimated speed ups in this Markov chain simulation. But that matches with the actual speed ups we did on the benchmark on the actual proteins where we simulated it, where we saw for the smallest protein factor 2, for the largest factor 7. So here I come to the optimum strategy, like the upper limit. So assuming we have all the information on the system, how can we pick the restarting points to improve it as best? So we kind of take the exploration-exploitation dilemma, and due to external information, we can solve the exploration part of the dilemma. So we can just exploit all the information which we assume we have. So this is not the real case. Generally, we don't have the Markov state model, but this is kind of the upper limit. If we had perfect information, how fast could we speed up our strategy? So what we do is take all our states. In this approximation, we have the transition probabilities between states I and J. And this equation kind of gives our strategy that if we have a state and we move to a state which is closer in this optimal time to the folded state, then we accept this move. And if it's further away, then we reject this move. So this we can represent as equation, and this as equation between these optimal times for each of the states, which we don't know yet, and these transition probability. We solve this equation, and we will get for each state this upper limit time, how fast we can get to the folded state, just from the Markov state model. So assuming we have that, so that's the upper limit. And the upper limit is a factor of roughly, let's see, roughly factor 2 faster than the best strategy which I simulated. Maybe more, depending on your system. So there's room to improve in this exploration-exploitation strategy. So I come to the conclusion what I did. So for these benchmark proteins, I pushed the boundary how far to push with these unbiased, like no external force bias strategies, and got to around 70 amino acids, but that still takes a lot of supercomputer time and GPUs. So this is one approach, and hopefully you learned something from this story. All this work was done mostly with Cecilia Clementi at Rice, Lydia CIIRC for the actual computational strategies, the computer engineering for the high throughput scaling, which Anthony Judd, Rutgers, and funding, and SF Welsh, and computational resources, mostly Summit. And these are the 2 papers which are showing the 2 aspects, the Markov chain simulations and the actual simulation of these computers on a supercomputer. So with that, I want to thank you for your attention, and do you have any questions?
Thank you very much. Questions?
Yes.
Sorry.
I have the question about this optimal time. So do I understand it correctly that this is for a certain scenario, like
Yes.
this exploitation?
Yes.
Exploration. So it's not a kind of physical limiter.
No, there are several assumptions. One assumption is we already know the whole Markov state model probabilities. So we have all the information. That's why it's an upper limit. Typically, we don't have all the information. Second approximation is that we do only this adaptive sampling steps for the exploration-exploitation. So it's a model of upper limit of a model, essentially.
What was the total simulation time you achieved for this 70 amino acid?
So the simulation time. So these are like in millisecond scale, the actual total simulation time I run. So these are parallel. So I used 50 GPUs in parallel. The total simulation times is in milliseconds. Yeah. But the time scales you can get from the Markov state models are longer because you're kind of combining them, and the time scale. So each simulation might be just aspects of these Markov state model. And if you combine these whole map of Markov state model, this timescale might be much longer. So that's what you match with the experimental. The experimental timescales are representative of to the Markov state model timescales, not to the computational timescales.
Was the condition for the convergence? At some point we had a plot. that was
Yes,
like,
I had like a thing
yeah,
like
goal
goal
achieved.
achieved.
Yeah.
So that depends on what exactly you want to do. In experimentalist case, you might look at your landscape and see if it matches what you're interested in, which is quite vague. So typically you just look at these plots. In my case, I looked, did we find the experimentally defined folded state as a benchmark? In other cases, you just might look at, is your Markov state model converged? No new state you find, even though by adding more computational resources on the problem.
Okay, thank you.
Any more questions? Yes.
Yes, thank you for that. Is there a good way to somehow quantify that the protein is folded, or the only way is to visually inspect the landscape?
So visually, you can definitely inspect it if you have a very deep minimum. So you look at the energy in this dimension reduced space, and if it's like 90% of your conformations are in this small part of your landscape, then that's kind of the folded, or assuming you already explored the whole landscape. Not every protein actually folds that way. Like IDPs have more smooth landscape. So essentially just the deepest minimum in this dimension reduced landscape, that's probably biologically important. To make it folded, you would essentially have to reproduce what the experimentalists do, just crystallize it or something like that. That depends on your assumption what exactly is folded, because on your experimental accuracy and so on.
So there is no universal way to take a big structure and say that it's folded.
It depends on assumptions. One is you already found the whole landscape. The second assumption is you look at the deepest minimas and check if that represents what you're interested in. If there's only one minimum, probably your folded state.
Any other questions?
And you also check the actual 3D structure. So if it looks like what's typically in experimental crystallized structures, probably folded. If it's just like wave around, might have an IDP part. So the IDP is like experimentalist representation of it's moving, like this distribution is more broad.